Okay, thank you very much for the invitation. Thanks for the intro. It's a great pleasure to be here. So yes, I'll be talking about a recent paper on discovering faster matrix multiplication algorithms with reinforcement learning. So the idea is to try to tell you a bit more about how we can use a particular technique in machine learning called reinforcement learning to discover new algorithms and by extension, solve math problems. So the way this project started is by asking a very simple question. Can we discover new provably correct and efficient algorithms for impactful problems using machine learning? So there are three keywords here, provably correct, meaning that we are trying to find algorithms that are correct for all instances and for which we have a certificate of correctness. So it's not like we're trying to find algorithms that work for some instances and for which we don't have any guarantees. We really want to find algorithms that are correct everywhere and for which we have a certificate of correctness. Efficient, meaning that we are trying to find algorithms with low computational complexity. And we were trying to work on impactful problems, or what we call root node problems. These are problems that if we're able to solve, then this can have huge implications on other problems, because these problems are a central component to many other tasks. If we're able to do that, if we're able to automate the procedure of algorithmic discovery using machine learning, then this can have a transformational impact, because these algorithms, as you know, they are used everywhere, from your smartphone to supercomputers. If we're able to improve the algorithms used on these machines, then this can have a huge impact. Now, obviously, it's not an easy task. How can we even formulate the problem of discovering new algorithms, provably correct algorithms? Like if you think about it as a search problem, how can we even start thinking about the search space of provably correct algorithms? This is a very difficult problem to model itself. And even if you're able to model that as a search problem, then this usually has a huge search space. So you're trying to really find a needle in a haystack, because if you think about the number of algorithms that are incorrect versus the ones that are correct, this is the number of correct ones is way smaller, right? Yeah, so this is a very challenging topic, I think. So I'll try to tell you a bit more about this today, and specifically to apply to the problem of matrix multiplication. Why did we focus on the problem of matrix multiplication? Well, because it's a root node problem. I think we all know how matrix multiplication is a central component of many other problems, like solving linear systems, training neural networks, simulation, and so on and so forth. But also, as I'll tell you a bit more today, this is a problem that has a relatively clean formulation, and for which we can use reinforcement learning techniques, as we'll come to. So the outline of my talk is going to be as follows. So first, I'm going to tell you a bit more about how can we formalize the problem of finding matrix multiplication algorithms as a machine learning problem. I mean, when we look at it from a first sight, this problem doesn't look like a problem that can be tackled using machine learning, but we'll see step by step how can we go towards this formulation. And then the second part of my talk, I'll tell you about 4 ingredients needed to make machine learning work in this problem, but also more generally in different math problems. I'll tell you a bit about the results we've got, and then some concluding remarks and hopefully a discussion. Okay, so first things first, I'm sure you're all aware of this, what matrix multiplication is, but let me just remind you and set the notations. So matrix multiplication for 2x2 matrices is defined as follows. You have your matrix A and your matrix B, which are size 2x2, and the result is matrix C. So what you're doing is, for example, for C11, A11 times B11 plus A12 times B21, right? So you have 8 scalar multiplications, which are stored in these H's, H1 to H8, and then you're distributing these H's to form your output C, okay? Now, this is the algorithm that we're all taught in high school and potentially college. And it was, for a very long time, it was thought that this algorithm is the best one to do matrix multiplication. There is nothing better than that, essentially. But in 1969, a German mathematician called Volker Strassen has shown that there is actually a better algorithm to do matrix multiplication. And he came up with this very strange algorithm to do matrix multiplication, which is on the right here. So what he did is essentially to try to combine entries together. So for example, by computing A11 plus A22 and then multiplying it by B11 plus B22, okay? And doing like 7 steps, seven multiplications, 7 combinations and then multiplications, and then distributing these edges in a very bizarre way. But eventually what you have is an algorithm that is correct. This algorithm is, you can check for its correctness, right? Through algebraic manipulation, you can check that this really gives you the expected result for 2x2 matrix multiplication, right? So it's an algorithm that is quite hard to come up with. I mean, it's quite unintuitive, I think. Why do you need to sum up A11 plus A22 and then multiplying by B11 plus B22 and so on? But it's one for which it's quite easy to verify its correctness, okay? So Strassen came up with this algorithm that uses 7 scalar multiplications rather than 8. And the very interesting bit about Strassen's algorithm is that it's not only applicable to 2x2 matrix multiplication. You can apply it to n by n matrix multiplication by decomposing your matrix into blocks of, or into submatrices of size n over 2 times n over 2, okay? And then you apply Strassen's algorithm on the blocks, okay? And you can do that recursively. So eventually what you're obtaining is an algorithm of complexity n to the power log base 2 of 7, which is roughly n to the power 2.81. Okay, so this was the first algorithm to go beyond the n cube algorithm to multiply two matrices. So the algorithm we all know for multiplying matrices is of complexity n cube. Okay, so this was very exciting because yeah, you could essentially like beat the n cube algorithm in a very fundamental task such as matrix multiplication. Now, what I'm going to tell you is how we can formalize this with the language of tensors, which is going to be very useful. How can we formalize the space of matrix multiplication algorithms, and how can we search in that space? Just like Strassen did it on a piece of paper, we can try to automate this and try to find algorithms to multiply 3x3 matrices, 4x4, and so on, and do this same idea of recursion. Okay. Okay. So first things. So first thing is the matrix multiplication tensor. So the operation of multiplying the operation of multiplying matrices is a bilinear operation, right? So just like linear operations, you can represent them as matrices. Bilinear operations, you can represent them as tensors, okay? So the operation of multiplying two n by n matrices can be represented by a tensor of dimension n squared by n squared by n squared. And the tensor that represents the operation of multiplying matrices is independent of the matrices that you want to multiply. So here we're talking at the operator level, okay? So this is a tensor just made up of zeros and ones, okay? It's a tensor made up of zeros and ones, and it's for example, the one on the right here for multiplying 2x2 matrices. Okay, so remember that for multiplying n by n matrices, the tensor that represents the operation for multiplying matrices is a tensor of size n squared by n squared by n squared. So in the case of n is equal to 2, you have a 4x4x4 tensor, and it's a tensor like that has entries 0 or 1. It has an entry of 1 at places where you read multiplications and you write them. Okay, so for example, here you're going to do a multiplication of A21 times B12, and you're going to write it in C22. So therefore, you have a 1 in the coordinate associated to A21, B12, right, and C22. Okay, it essentially tells you where do you read the entries to multiply and where do you write it, where do you write the result. Okay. So just like we saw previously, the operation of multiplying 2x2 matrices involves 8 multiplications. Therefore, this tensor has 8 ones and the rest is zeros. Okay, so you can do that for all the scalar multiplications that you have, and therefore you have the 8 ones in your tensor. So this tensor, and I'm emphasizing on this tensor represents the operation of multiplying matrices, and it's not like is independent of the matrices that you really want to multiply. Okay, so that's the operation of multiplying matrices that we can characterize with this tensor. How about algorithms now, right? We want to find algorithms to multiply matrices. So what we'll focus on today is algorithms that can be written as low-rank tensor decompositions of this tensor, okay? So let me try to unpack that a bit. So you have this tensor, and I'm claiming that whenever we get a decomposition of this tensor into a sum of rank 1 tensors, then you're going to get automatically an algorithm to multiply arbitrary matrices. Okay, so what is a low rank decomposition of a tensor? It's actually like a very simple extension of what you all know, which is a low rank decomposition of matrices. So remember that rank decomposition of matrices, you just write them as sum of UQ VQ transpose, right? So here we're doing just we're extending this to 3 modes, where we have here UQ tensor product VQ tensor product WQ. Okay, this is UQ tensor product VQ tensor product WQ is a rank 1 tensor, right? Where UQ, VQ, and WQ are all vectors of size n square. Okay, so UQ is of size n square, is a vector of size n square. So therefore, the size of UQ tensor product VQ tensor product WQ is just a tensor of size n square by n square by n square. Okay, and then you're summing this r times. This is just pictorially represented in the bottom of the slide here. Like UQ is represented with this color, PQ with that, and WQ here. Okay. And what I'm claiming, as I said, is that whenever you have a low rank or a decomposition of this matrix multiplication tensor, then I can take this decomposition and then convert it into an algorithm for multiplying arbitrary matrices. Okay. So the way you do this is through this formula. Okay, so you want to multiply 2 matrices A and B, then this summation here gives you an algorithm to multiply matrices A and B, and the parameters of this algorithm are UQ, VQ, and WQ. Now the important bit here is the rank, or like the rank of this decomposition. The lower the rank, the better the computational complexity of the algorithm that you're finding. Okay, so R precisely characterizes the computational complexity of your matrix multiplication algorithm. Okay, now this, as I said, this algorithm is not just to multiply n by n matrices. You can multiply matrices of arbitrary size through recursion, just like we saw Strassen's algorithm. We can also apply such algorithms for arbitrary size by decomposing into submatrices and so on and so forth, as we saw. Okay, so in light of this new language of tensors, the matrix multiplication tensor representing the operation of multiplying matrices, and then decompositions of this tensor corresponding to algorithms, the result of Strassen, like the algorithm of Strassen for multiplying 2 by 2 matrices, is a rank 7 decomposition of the matrix multiplication tensor corresponding to multiplying 2 by 2 matrices. Okay, so that's essentially like the equivalent of Strassen's algorithm with this new language that I just described of tensors. Okay. Now, as I said, there is this equivalence between algorithms and low-rank decompositions. Let's see more concretely a bit how we translate from one to the other. So as we said, the first line of Strassen's algorithm is A11 plus A22 times B11 plus B22, and then we're distributing them in that way. So if we want to convert this algorithm into a rank decomposition, then we're going to take the coefficients in front of the A's here, we're going to put them in the U, and then the coefficients in front of the B, and we're going to put them in the V, and then how we distribute this H1, which we're building, and when we're going to see where H1 is used, and then we're going to put here 1001 because it's used in C1 and it's used in C2. Okay, so essentially U and V tell you how you multiply entries, how you combine entries in A and B, and then the W tells you how you distribute those. Okay. Okay, So we converted, therefore, the problem of finding algorithms for multiplying matrices into a math problem, which is to find low-rank decompositions of the matrix multiplication tensor, right? That's our goal, to find low-rank decomposition of the matrix multiplication tensor. Once we have found that, then we have an algorithm for multiplying arbitrary matrices, as I said before. Now, unfortunately, unlike matrices for which there are polynomial time algorithms to compute the rank, for tensors, even like just three-dimensional tensors, there is no polynomial time algorithm to compute the rank of such tensors, right? And this is precisely where we're going to use machine learning for. We're going to use machine learning to tackle this hard problem of computing the rank of tensors, and in particular of the matrix multiplication tensor. So the way we're going to cast this problem as a machine learning task is through a game, essentially. Okay, so a single player game. Our board is going to be a three-dimensional tensor, which corresponds to this matrix multiplication tensor. And then at each step, what the player can do is to subtract a rank 1 tensor, okay, of its choice. Okay, so it can choose any rank 1 tensor. It subtracts it from the board, from the current state, which we start with the matrix multiplication tensor. So you get then a new tensor, and then you're going to repeat this game r times. Okay, so we're going to repeat this game for a fixed number of times. Now the player is going to win if it reaches the zero tensor, the tensor which is made up all of zeros in the tensor. Okay. So it's not very hard to see that whenever you get a tensor that is all zeros, then you actually get a rank decomposition of the original tensor, which is the matrix multiplication tensor. Okay, so therefore you win because you have found a decomposition of this matrix multiplication tensor. Now we don't want just to find any decomposition of the matrix multiplication tensor. We want to find the most efficient one, or the one that has the smallest number of components, right? So therefore, we give a negative reward each step the agent takes. Each time you subtract a rank 1 tensor, then you get a penalty. And then at the very end, let's say you don't reach the zero tensor, then you compute an upper bound on the residual tensor, and then you sum up that final reward to make sure that you're penalized whenever you don't reach the zero tensor. Okay, so it's a relatively simple game to describe, where you have this three-dimensional board game, and then you have to choose essentially which rank 1 tensor you remove, and then you update your board, and so on and so forth. Okay, now despite the simplicity of the description, it's actually quite a hard problem, and the difficulties are as follows. So you have a huge action space. You actually have an infinite action space, because at each step you're going to you have an infinite number of rank 1 tensors you can subtract. But even actually, if you're discretizing your action space, even then the number of actions is going to be very, very large, as we'll see. There is no training data, so unlike games like Go, for example, for which when you have demonstrations online of like very good players, for which you can get some intuition or start to do some pre-training on these demonstrations, there is no such demonstrations that you can rely on. There is only one tensor to decompose, so this is a slightly unusual setting in machine learning, where you only care about this one specific tensor, or this one specific instance that you want to solve. So there is really a lack of diversity in the training framework here. And then there are a number of symmetries associated to the problem. For example, you can permute any rank 1 tensor, you'll get the same decomposition. You can permute slices of your tensor, you get the same rank, and so on. So this is a mathematical object, and it can either be a difficulty or something that you can leverage in your architecture in order to improve the training procedure. Okay, so now, maybe to be a bit more concrete, let's try to compare a game like Go, for example, which is a big challenge a few years ago, and for which like AlphaGo was a solution that that beat the best human on this game. So let's try to compare the game of Go to that game. So in this case, the main thing I would like to highlight here is the action space being much larger than that of Go. So in Go, you have a 19 by 19 board. So your action space is just 19 times 19 plus 1. In this case, if you discretize your action space, as I said, to allow entries, for example, to be only -1, 0, 1, then you cannot just enumerate all the actions that you have. For example, for the case of 2 by 2, you have 10 to the 8. For 3 by 3, you have 10 to the 18, and so on and so forth. Okay, so you really need to be able to go beyond this procedure of enumerating all your actions, picking the best one, and so on. Okay. Okay, so the approach that we're going to rely on is a Monte Carlo tree search approach, where at each step we're going to try to see or like evaluate which rank 1 tensor is the most promising one, and then again like updating the state, running many simulations, trying to evaluate the one that is the most promising, and so on and so forth. The important bit here is that the tree search that we're going to do at each step is going to be guided by a neural network. And the neural network is going to be really the key in this whole procedure to try to identify which rank 1 tensor is the most promising one, okay? So this animation here is actually shown for Go, but you can imagine that in our case, as I said, the action space is way larger. So the number of things you would need to evaluate at each step is really like much larger than what can be shown on this slide. So the agent that we're going to propose, AlphaTensor, is based on AlphaZero. Okay, and AlphaZero is this reinforcement learning algorithm that was shown to perform really well on games like Go, chess, and shogi. But it's a general reinforcement learning algorithm, and we'll see like it can be applicable to other environments. So I'll try to describe briefly what AlphaZero is about. So AlphaZero is essentially like relying on two components: actors and the learner. Okay, so you can think of actors as different machines playing independently many games in parallel. Okay, so at each step, what you're doing is that you're, as I said, you're doing like many simulations. You're doing like Monte Carlo tree search simulations, picking the most promising like action, and then updating your board and so on and so forth. So in the beginning of the training, the actors are playing games essentially at random because the simulations that you're doing are random. Okay, so the games that you're going to generate are not going to be very good. So in the sense of, like, for example, in our case, the games that you're going to generate are going to produce decompositions that have very high rank. But that's fine. That's just the beginning of training. So what you're going to do at the next step is to send these games that you have accumulated in each of these actors to the learner. Okay, and then the learner, what's going to try to do is to reproduce or to imitate the games that have been played by the actors. Okay, so the learner consists essentially in a neural network, and the neural network tries to output two things: the policy and the value. The policy is essentially what was the action that was taken, and the value tells you how promising is the current state in which I am. Okay, so let me repeat that. So the input to the neural network is going to be a state sample from the games that have been sent to you by the actors. And then the output of the network is going to try to predict what was the next action which was taken. Okay, and the value is just how promising is my current state. So my state, in the case of this tensor game which I presented, is a tensor. Okay, is the current tensor in which I sit. So the value is going to correspond to an estimate of the rank of this tensor. Okay, and the policy is just going to be what is the next rank 1 tensor, which I'm going to subtract from this tensor. Okay, so I'm emphasizing here on the fact that it's just trying to imitate the games that have been sent to you by the actors. Okay, now why is this useful? Well, you're going to take this neural network and then you're going to send it back to the actors. Okay, and now when the actors are going to play games again, they're not going to do simulations at random, but they're trying to they're going to use the neural network in order to guide the search. Okay, so you're going to use the policy and the value in order to try to explore places of the search space that are most promising. Okay, so the idea is that you start as a, like you use these policy and values as a baseline, and then with Monte Carlo tree search, hopefully you get a bit of improvement over the values that have been provided to you by the neural network. You can think of the Monte Carlo tree search as a policy improvement operator. So like it starts from the policy and the value that have been proposed to you by the network, but then they explore a bit around this, Monte Carlo tree search explores a bit around these values in such a way that you can improve over the values that have been provided to you by the network. After you play these games that are in which you use Monte Carlo tree search and the search is guided by the neural network, you're going to send the games again to the learner, and then the learner is going to try to use these improved games to try to imitate those, and then you send the network, after you do some gradient steps, you send the network to the actors, and then hopefully Monte Carlo tree search improves a bit over that, and so on and so forth. So this is therefore what you get, a self-reinforcing loop where you start really from random games, and bit by bit you really can start playing like either Go or chess really well, without any human demonstrations. Okay, so as I said, we're going to rely on this algorithm, AlphaZero algorithm. But like applying AlphaZero from scratch is not going to work really, because as I said, it has like some major difficulties, like for example, the action space and so on. So what I'd like to talk to you about is like 4 ingredients that are important to make this work, to make this procedure, AlphaZero procedure, work for our problem, the tensor decomposition problem, but also beyond in math problems. So the ingredients are synthetic demonstrations, diversifying your target, train a generalist agent, and then deep and tailored architecture. Okay, so the first ingredient is synthetic data. It was like in our case, it was really important to not only rely on the games that have been played by these actors, but also to generate synthetic data, especially in the beginning of training. This is very helpful. So this is like tensor decomposition belongs to this class of problems that are like one way. Like one way is really hard, but the opposite is really easy. So getting a decomposition from a tensor is really hard, as I said before, but the opposite is easy, right? So if you generate at random a decomposition, then you can get the tensor associated to this decomposition in a really easy way. So therefore, what you get is a procedure to generate an infinite number of tensor factorization pairs, or like a training data essentially. So you can generate random decompositions, have the tensor associated to it, and therefore what this pair gives you a demonstration that you can use for training your system to decompose tensors, right? And this is precisely what we do. If you have symmetries in your problem, then you can also incorporate any of the symmetries. Like for example, let's say you want to find decompositions that are like if you have UVW in your factorization, then you also have VWU or WUV. Then these are things you can incorporate in your training data, and therefore the neural network will be biased towards decomposing tensors in that particular way. So so what we arrive to essentially, like the procedure that we arrive to is a procedure where we train the neural network based on the games that have been played by the actors, but also relying on these demonstrations. Okay, so this is the setting that we found to be the best in terms of training that neural network. Now, obviously, the difficulty with this is that the distribution of synthetic data can be far from that of the target. So the matrix multiplication tensor is a tensor that is highly symmetric, for example. This is quite different from the random demonstrations that you're generating in this particular way. right? So that is a potential difficulty, but we found still this procedure to be really useful, especially at the beginning of training. The second ingredient is to diversify your target. So as I said, this is a slightly unusual setting where you really care about decomposing one tensor or getting a system that works really well on one particular point. And this is actually like quite common in different math problems where you care about just proving this one theorem, this one Millennium Prize problem, for example, or this one theorem that you really care about. Now, this is a bit different, as I said, from machine learning setup, where you care usually about the average performance across different data points. Now, what you can do is to express the tensor that you care about, or the particular data point that you care about, in different equivalent ways. So what we can do in this particular case is to do some change of basis, right? So you can take your matrix multiplication tensor that you care about, and then you express it in different equivalent ways. We know mathematically that when you express this matrix multiplication tensor in an equivalent way, then you're going to get a tensor with the same rank. But the neural network sees this new tensor as a completely different tensor, right? So once you decompose a tensor in a different basis, then you can propagate the information back to the matrix multiplication tensor. Pictorially, like why this can be useful is that you're essentially like shifting towards your training data, this random training data, as we described previously. Like when you generate these matrix multiplication tensors, you're essentially like getting some if you apply a random change of basis to these matrix multiplication tensors, then you're getting closer to the distribution that you have in your training data. Okay. So the third ingredient I'd like to talk about. Sorry, I'll probably just open the lights because it's quite dark here. Okay, so the third ingredient I'd like to talk to you about is to train a generalist agent rather than several experts. So what you could do is you can just train a neural network or an agent to decompose the 2x2 matrix multiplication tensor, for example, and to try to rediscover Strassen's algorithm. But what we found, and that will work fine, right? But what we found to be much more better in terms of performance is to train a neural network or an agent to decompose all these tensors simultaneously, because then there is like very interesting and positive transfer happening between the different tensors. So the different tensors we consider are tensors of different size. So for example, for multiplying 2x2 matrices, 3x3 matrices, 4x4 matrices, and so on, and then rectangular ones too. And we train all these simultaneously. So what will happen is that the agent in the beginning will find algorithms for multiplying small matrices, and then reuse these techniques for larger tensors and so on and so forth. So this procedure of transferring from small to large is something that we did not impose explicitly, but that the neural network itself finds it to be useful to tackle the problem in this particular curriculum. Now, there are some transfers that happened between different targets, which we find to be very interesting and surprising. So for example, I'm making this up, but like there are targets for which you don't have any mathematical relation. So for example, 3x3 times 3x4, and then 4x4 times 4x4. It turns out that training jointly these things together, so training to decompose these tensors jointly, is much better than training them one by one. Okay, and the way you could do that is by doing an ablation analysis where you remove one of them from your training target, and then you definitely get a big boost in terms of performance if you train them jointly. Okay. So all in all, what I'd like to kind of like emphasize on here is that it's in this particular case and in many math problems, it's better to train a generalist agent rather than just focusing on the particular target that you care about. So this is an improvement in terms of performance, but there is also an improvement in terms of efficiency, where you could obviously like get results much quicker if you train everything at once. So I described here the particular like transfer that happens with different sizes, but we also did that for different fields. So you can train to find matrix multiplication algorithms on different fields simultaneously, and you get also a boost in terms of performance compared to just training them each one by itself. The fourth and last ingredient I'd like to talk to you about is the architecture and the importance of training deep and tailored neural networks. So one approach could just be to train a multi-layer perceptron, for example, on this particular task, but that won't just work, right? So you really need to incorporate some of the prior knowledge you have about the problem. And I'll tell you just very briefly how you could do that in this particular case. So remember that the neural network that we would like to consider here has two outputs: the policy, which tells you what is the next action to take, and then the value, which evaluates like the promisingness of your current state, or in this particular case, the value or the estimated rank of this tensor. So the architecture that we rely on has a torso. So you take this tensor, you feed it to a torso, and then you have two heads. So one torso and two heads, policy and value. So like what we found out to be very important is the architecture that you use in the torso. Okay, so the particular architecture that we used in this case takes as input, as I said, this tensor. And then the first thing we do is to project this tensor into three grids of features. One grid of feature that is responsible of two modes, UV, and then another one VW, and then a third one UW. So you can think of it as like intuitively as just maybe different viewpoints of your tensor. And the reason why we're doing these projections is essentially mostly for reducing the dimensions, right? Because we need to do a lot of simulations, so we cannot really work with this large tensors. So then once you have these three grids of features, then you are going to do some attention operations on them. So what we do is the attention operation on sets of features belonging to a pair of grids, right? So what you could do is attention between every cell and every other cell. But first of all, this is something that doesn't work really well, and then it's also quite computationally intensive. What we found out to be useful is to do attention between entries that belong to the same slice, right? So intuitively, what you have is that entries that belong to the same slice are more related to each other than entries that belong to different slices, right? So in a way, you're doing attention between entries of the tensor that are more related to each other. And also you're incorporating in this way, this invariance, which I talked about before, that if you permute two slices of the tensor together, then you have the same rank. So all in all, the system we have is as follows. So you have this matrix multiplication tensor. The first thing you do is that you sample a random change of basis, and then you're going to do this Monte Carlo tree search based on the neural network that you have. You're going to pick the rank one tensor that you chose, and then you're going to play this game till the very end. You're going to send these games to the learner. The learner is going to sample both from the games that have been played by the actors, as well as from the synthetic demonstrations that we've built. You're going to train the neural network to predict the policy and the value, as we described before. You're going to update the neural network by doing a few gradient steps. You're going to send that back to the actors, and so on and so forth. The actors are going to use this neural network to improve the search, and so on and so forth. Okay. So that's the overall system. Now let's look at the results. So as I said, you're going to train a neural network or an agent. You're going to train AlphaTensor to decompose all these sizes simultaneously. So just to kind of like remember that if you find an algorithm, or if you find a decomposition for any of these sizes, then you have an algorithm to multiply arbitrary matrices through this recursion procedure. Now, for each one of these sizes, what you have is a tabulation of what is the best known rank, what is the best known algorithm to multiply these matrices of this size. Okay. So we, as I said previously, we work in different fields. So here we work in fields of characteristic 2 and in R. And so we train this AlphaTensor like system. We train the AlphaTensor system, and in the beginning, it essentially like finds the classroom algorithm, and then at some point it rediscovers Strassen's algorithm. And if you continue training, again and again, what will happen is that you will recover the known algorithms, and then at some point you will go beyond the existing algorithms. So for here, for example, it found an algorithm to multiply 3 by 4 times 4 by 5 matrices with 47 multiplications rather than 48. And you continue, and then you're going to find algorithms that go beyond the state of the art. Okay, so these algorithms are algorithms that outperform the known algorithms. So for example, for 2 by 2, this is Strassen's algorithm. And one particular example that we were very proud of is the 4 by 4 matrix multiplication algorithm, which the best known was due to Strassen, the 49. Like it uses 49 multiplications, 7 times 7. It corresponds to like applying Strassen's algorithm twice. And what we found is that in fields of characteristic 2, AlphaTensor was able to go beyond this 49. This algorithm that involves 49 multiplications, and found an algorithm that only uses 47 multiplications. So that means that the algorithm that you're getting is of complexity n to the power 2.7. So let's try to visualize quickly like what these algorithms look like. So this is the algorithm to multiply 4 by 4 matrices in fields of characteristic 2. The one that involves 47 multiplications. It's, as you can see, it's actually quite hard to interpret. As I said before, this is even harder really to interpret than Strassen's. But again, like it's relatively easy to check the correctness of this. So anyone can really take it and then do the manipulations by themselves, and then see that the algorithms that you're getting are precisely correspond to the matrix multiplication formula that we all know. So the results that I shown, like remember the rows that we had corresponded to the different sizes. Well, we don't just find one algorithm for multiplying like these matrices, but we found thousands of inequivalent decompositions for each target, or thousands of inequivalent algorithms for each target. The notion of equivalence is something that I don't think I will go through now, but essentially you can think of it as that there is a like whenever you find an algorithm, you can generate a lot of equivalent ones by, for example, permuting some factors and so on. So what we find is algorithms that go beyond this group of symmetry that can like essentially like you cannot apply these transformations to get these algorithms. So we open source the data set of factorizations. And we hope that mathematicians and people working in the field will look at them and try to maybe improve over them and make and try to see like understanding the symmetries and so on. There is also an important benefit of generating these diverse algorithms in the sense that you can actually like improve over like you can try to use this diversity to improve the ranks of tensors that are even of larger size. So what you will do is that you take the low rank decompositions that you found, and then you can recombine them in some way. I won't go into the details of that, but if you have a lot of diverse decompositions, then you are able to improve even further than if you just had one decomposition for each of the targets. So the procedure of multiplying matrices here, or like the procedure that we use to decompose these tensors, can be really used to decompose arbitrary tensors, not only the matrix multiplication tensor, right? So you can train that on arbitrary bilinear maps. So what we considered here is, for example, the skew-symmetric matrix vector product, which is a particular bilinear map. And then what you have is a decomposition for each n. So here, what we'll get through AlphaTensor is a decomposition for each n. And you can see that what AlphaTensor finds is for each n is a decomposition that has a very specific structure, right? So you can then try to extrapolate the structure, and then you therefore get an algorithm for multiplying this skew-symmetric matrix vector product. And it turns out that the algorithm that we find improves over the previous best known result. So this is one specific example where we can study, because like this is a bilinear map. So again, it can be represented by a tensor, and you can like try to find decompositions and so on. We also have another example in the paper where we study the circulant matrix multiplication. Then you can rediscover the Fourier basis, for example. Okay. Now, going even beyond that, so you can really consider things that are a bit wild, in the sense that we're using here reinforcement learning. So you don't need to have the reward being like differentiable or anything like that. You can really have a stochastic reward, and like as long as you can compute the reward, that's essentially fine. So what we did to highlight this possibility is to add a reward that is essentially the latency of the algorithm on hardware that you care about. So let's say, for example, you care about multiplying matrices on GPU, certain type of GPU, then in addition to the reward I just described previously, you can try to multiply these matrices on this GPU, and then use the latency as a signal to find the algorithms that are the fastest on this particular GPU. Okay. So what we did that precisely, and then the algorithms that you find are like outperform or like lead to some speed up compared to the normal matrix multiplication on the specific hardware for large matrices. So here we're starting from 8,000 by 8,000. So you think of this as very large matrices, and it also improves slightly over Strassen's algorithm for multiplying matrices. Now, we tested that on a V100 GPU and a TPU, another type of TPU called TPU version 2. And the interesting bit here is that the algorithms that are found for the GPU case. So if you try to optimize essentially the algorithm for GPU, then and then you try to use this algorithm on a TPU, it wouldn't be as fast as if you optimize it on TPU and then test it on TPU. So the algorithms that are being found are essentially like quite specific to the hardware that is being considered here. I'm going a bit fast over this because I'm conscious of the time. So this is my last slide. So remember that the inspiration that we started with is essentially, can we try to use the fantastic achievements we've done in playing games such as, for example, Go, chess, shogi, in other very hard combinatorial problems and algorithmic discovery problems. I hope I convinced you that machine learning has an important role to play in this very hard combinatorial problems. Now, there are some limitations associated to the approach which I described. In particular, we had to discretize the search space. This can essentially lead to missing out on good algorithms, obviously, because we don't have any theorem that tells us that by discretizing we're not losing anything. Obviously, in finite fields, then we're not losing anything. But if you consider infinite fields, and that's the case, there's no optimality promise in the sense that you're not getting any lower bound. You're just getting an upper bound on the right, but you're not getting any lower bound. And I'll conclude with this, really, is that what is, I think, most exciting about this approach is the generality of it, in the sense that you can tackle problems such as like different bilinear operations. You can discover algorithms for other tasks. You can consider this like in other search problems. You can tackle like a relatively complicated space such as finite fields, and consider like objective functions that are relatively wild, such as, for example, runtime, and potentially like going beyond that, memory, and so on and so forth. So we think that, as I said, like this machine learning guided search procedures are going to be very useful to find new algorithms and to tackle hard combinatorial problems. If you're interested about these results or would like to delve deeper into that, please look at our paper that was published in October 2022. Thanks a lot for listening.
All right, thank you for the nice talk. Let's thank the speaker.